All right, guys, so here's our organic compounds. We saw some of this already in lab. We'll be doing a little bit further study of it today and finish it out with acids and bases at the end. I do want to remind everybody I did send a link to a review on the acid-base relationship because usually the way it happens, our last 2 minutes of class, it seems, we're having to squeeze in acid bases. So I've got that video out there that I sent you. It's about 7, 8 minutes. It pretty much details all the specifics that you would need to know and how you would be questioned on these acid-base relationships. So as I'm recording this session, I do want to ask that you turn your cameras off just for privacy reasons. We don't want anyone on camera when this video is distributed to other classes. So do turn your camera off, please. And if you don't realize your camera's on, just look at your menu and it'll show you that your camera is on versus off. Okay, so here we go. First off, the difference between a molecule and a compound. We use these terms actually interchangeably, and not to confuse you, but it's just commonly done. But by definition, I think it's only right that you know the specific definitions of these. A molecule is when you get two or more like atoms coming together, like two oxygen or two hydrogen atoms, that kind of thing. And a compound will be different atoms coming together. But yeah, we use the word molecule just the same as a compound conversationally, but just so you know the true definition. When you talk inorganic versus organic, anything organic is going to be containing carbon and hydrogen. Carbon as that backbone, whereas inorganic compounds have no carbon at all. With the crazy exception of CO2, don't ask me why. That's just there's always an exception. Always, always, always. But yeah, you can know for sure if you're asked a question, which of these compounds is inorganic, right? It's not like you have to memorize things, but I think it's common knowledge that water does not have carbon, right? Water is H2O, two hydrogens and one oxygen, no carbon going on in water. So it's inorganic. It doesn't mean it's bad, it just means it's not organic. The same with salt, sodium chloride, for instance, potassium chloride, there's no carbon there. Acids and bases like hydrochloric acid and sulfuric acid, no carbon there. Base, sodium hydroxide, no carbon there. So they're all inorganic. Whereas the big players here that we're talking about, especially in this chapter, here we go. Carbs, lipids, proteins, nucleic acids. Guys, this is what makes up your cells. This is the physical structure of your cells. Therefore, they're all organic compounds. And guess what they all contain? Carbon backbone with a whole bunch of hydrogens. So that makes them organic. All right, so getting into this slide again, here's the main players, of course, that make up your body. And guess what? These four main players, carbon, oxygen, hydrogen, nitrogen, guess what makes up organic compounds? Carbon, oxygen, hydrogen, nitrogen. So again, we're just confirming this being a good 96% of your body, if you want to include calcium, phosphorus, up to 98. But yeah, these are the major players. This is what you need to know. These four right there. And the trace elements, of course, would be everything else. Here's some little bit of info on vitamins, minerals, fiber. Realize which vitamins are considered water soluble versus fat soluble. That could be thrown in as a test question, especially those fat soluble vitamins, because that's our family of fats that we'll see when we get to the lipids. Vitamins A, D, E, and K. Realize vitamin K is not the same as potassium. Vitamin K is a clotting factor for our blood, so it's not potassium. Just know that difference. Minerals such as calcium, magnesium, phosphorus, sodium, potassium. Guys, this is what helps the body run, right? This is no doubt what makes the body run properly when in the right ratio and they're transported across the cell membrane in the right way. That is what physiology is. You'll get to learn, especially in A&P2, what makes a healthy body, of course, is first and foremost the structure. The structure being, do you have all the necessary organic compounds to build that cell, right? Number two, do you have the necessary minerals / electrolytes also to help those cells run properly, right? Then you've got to have the number 3, which is the communication between cells. And that's what we're going to get to in chapter 3. That's what transport is. So if you don't have structure, I mean, let's talk straight science here, straight medical science. If you don't have the structure, which in this case we're calling nutrition, to be honest, you're going to eventually get some kind of disease, something going on wrong, right? A diagnosis eventually, if the structure is not there, because structure determines function. We've said that day one. The structure being the nutrition of the cell, the chemistry of the cell, these organic compounds, all these minerals that are necessary, everything like that. That's all structure. And this, guys, is where our food today, compared to 100 years ago, is big lacking in minerals. If we have any cooks in the crowd here today, you guys are making your own broths, your own chicken stock, beef stock, that kind of thing. That is a great source of minerals coming out of those bones, let me tell you. And breaking down those tendons and everything, getting those good proteins, that is good health right there, let me tell you. Doesn't take much to make your own stock, but boy, you can use it all over the place. Very, very useful to get a great source of minerals. Taking vitamins is great too, but guess what? Unless you're taking expensive vitamins, not the buy one, get one at Walgreens or Walmart. But if your vitamins are expensive and they hurt to purchase them because they're so darn expensive, then you're probably getting some good minerals and vitamins and such because they absorb properly in the body. And that's why they're expensive. The cheap ones, they pack them so tight with chemicals. Guess what? You're going to take that pill, you're going to take that one a day. And that one a day is going to come out of you once a day, right through. It's not even going to break down, to be honest. So yeah, vitamins are a good source of supplement, but food is where it's at. Good food, whole food, right? Real food that comes out of the ground, that kind of thing. Nothing packaged. That's what America has become so fascinated with. Everything so fast and easy and packaged and frozen. The minerals and vitamins in there are there, but they're not in the highest amount. That's the key. They got too many other chemicals there competing. So yeah, real whole foods are where that's at. Minerals is where nutrition really, really needs to be picked up, especially in our country. For fiber, difference between soluble and insoluble, just they're both good. First of all, you got to have fiber in the diet. Soluble fiber slows digestion, lowers the risk of diabetes. Insoluble just gives the bulk in stool, promotes a great GI movement, great GI tract. I laugh all the time because when I was in practice, let me tell you, and if you're working in a hospital, you know what I mean. You meet a lot of grumpy people, right? And let me tell you, these people, they may not have pooped for 2 weeks. And you tell me, would you be grumpy or what? So these people are all over your case, and doesn't matter what you do, they're still unhappy with you. They probably just need a good poop. So yeah, it's a shame that diets are not more balanced, but yeah, you got to have that insoluble fiber to promote that bulk. For minerals, again, for electrolytes specifically, this is these that carry an electrical charge like sodium, potassium. This is what runs your consciousness, runs all of your mechanical action in your body. It's a big deal. Got to have sodium and potassium. When people are put on a low sodium diet, that's no problem if you got heart conditions, blood pressure, whatever. But you know what? Patients sometimes take that way too far. Instead of going low sodium, they go no sodium. And they think, oh, I'm going to beat that doctor. I'm going to show off and I'm not going to add salt to anything. Well, that's a horrible idea. Guess what? Your body's going to shut down slowly. And it's not a good thing. People that go no sodium or extremely low sodium, that's not healthy at all. I mean, I can't imagine a doctor alive that would ever say that a no sodium diet or very little sodium is going to be a good thing. I mean, that doctor needs to be removed because physiologically speaking, guess what? Your cells will not have an electrical gradient if you don't have any sodium, and your heart's going to stop, and your muscles are going to stop, and all your organs are going to shut down. So you definitely need sodium, just not too much. And certainly if you're drinking water, that's how it's balanced in the best way. If you're not going to drink water and you're eating a lot of sodium, heck yeah, you're going to have high blood pressure. No doubt there. Okay, breaking down our organic compounds, we need to know which one of these words represents a polymer and a monomer. So these four words are going to be the big guys, right? Every one of these is considered a polymer, which is made up of many, many, many building blocks. Whereas a monomer is the smallest subunit that these will break down to. So from lab, you tell me, I'm not going to put it on the slide because you already should have learned it. What does a carb break down to become at its smallest unit?
Glucose.
Glucose, right, which would be a monosaccharide. So glucose is good to know, but also see on a test, it's going to be probably written as a monosaccharide. So right, carbs break down to become, at their smallest unit, a monosaccharide. What about proteins? What do proteins break down to become to the smallest unit?
Amino acid.
Amino acids, awesome. If you don't know these four right out of your head, if right now you can't write those on a note card or a sheet of paper, I will say, and maybe this will scare you, you are in trouble. It means you didn't get something or everything you needed. You need to be able to write these down. Simple things like this, I promise you they're on the test. Lipids, what do those break down to become? We got fatty acids and a glycerol molecule. That was a little more complicated because lipids are very diverse, very big, tons of energy in lipids. Holy cow. We're going to see it just a bit. But lipids break down to become fatty acids and glycerol at their smallest unit. The smallest units that I'm talking about would be called the monomer or the subunit, whereas the largest is the polymer, which are these words. So carbohydrate is a polymer, and since it's a carb, it's called a polysaccharide. Proteins are polymers, right? And since it's a protein, we call it a polypeptide. So polysaccharides are this, polypeptides are that. But they're still called polymers because that's the generic term. Lipids, right? Very, very, very big family. We're going to see that, but that's the polymer. The monomer would be the fatty acids and the glycerol we just talked about. Last one, nucleic acid. That's the polymer. What does it break down to become?
Nucleotides.
Nucleotides, perfect. And that one we know less about, in class at least. We don't really talk about it a whole lot. We will in chapter 3. We'll cover the DNA, RNA, and ATP a little bit more. That's what nucleic acids are. DNA, RNA, and ATP. So let's dive in. There's our words again, a macromolecule and a polymer. Really just kind of the same thing. Macro just means big. Polymer means big, so they're really just saying the same thing. There's another word association. Please, again, recognize how these terms are used. Monomers are linked together in anabolism using dehydration synthesis. Polymers are broken down from big to small using hydrolysis. Now let's clue in on this term here. If you had something like that, let me get this going on here. If you had something like this on a test, this picture, right? And it was not labeled dehydration synthesis or hydrolysis, and you were asked to drag and drop those words to label each side of the equation here, each side of the reaction, could you do it? If all you saw was that water molecule being pushed out or brought in, would you be able to label this with those terms? Be honest with yourself. So realize that dehydration synthesis means that water is being given off. It's leaving, which would be that top one. And hydrolysis is being water being added in to the reaction to break something down. So again, try to study that picture. Make sure you would know how to label that if given the opportunity to drag and drop these terms to get each side of that reaction going. Okay, moving on. Here's another way to look at it. If we have two monomers coming together to make a dimer, that's just another term, another generic term. If these were two amino acids, let's say, and we wanted to join them, right? That'd be a dipeptide. Or if these were two carbs, right? That's a monosaccharide here, a monosaccharide there, that'd be a disaccharide here. So get used to those terms right here. In this case, it's just a dimer, generic. unit or a molecule of two things coming together. So anyway, when we join things together, we lose that molecule of water. This pathway is dehydration synthesis. We're joining together, right, to make one molecule. In the case of hydrolysis, we take a bigger molecule here and we break it down into the two monomers. That would be hydrolysis. So since this is a picture out of the book, imagine that word hydrolysis not being there. If you saw this picture on a test, and I'll tell you, if I was making the test, I'd for sure put this picture on there because it shows everything. If you saw this picture alone, would you be able to label it as hydrolysis or dehydration synthesis? Be honest. You got to look at where the water is going. Water is being put into the reaction. See that right there? Whereas the previous one, water has been given off. So that's why that word dehydration is there. Water is being given off. So I tell you what, if this really messes with your head, because to be honest, in college, it probably would have messed with my head. I've been teaching this for 20 years, so it doesn't mess so much anymore. But learn your favorite. You're going to see it, I promise. Learn which one speaks to you the best. And then just know the other is the opposite to make sure you get them all straight. Okay, specifically for carbs, we got three sizes here that we like to talk about. Monosaccharides, disaccharides, poly. Which one's the biggest?
Poly?
There you go. Very, very good. Which one's the smallest? Mono, right? So if we take monosaccharides together and build them up to become a poly, what cycle is that? Is that hydrolysis or dehydration synthesis? Taking monos together to build them up to become a poly. Synthesis, perfect. If we take a poly and then run the opposite direction, break that poly down to all these other monosaccharides, what cycle does that? Breaks down. Hydrolysis, there you go. That suffix lysis is the key. Lysis means to break up, right? Or burst. And when breaking things down, would that be catabolism or anabolism?
Catabolism.
Catabolism, right. Why might we be releasing energy as well by breaking things down, breaking those bonds? Yep. Would that be exergonic or intergonic?
Exergonic.
Very good. Very, very good. Exergonic. Releasing energy is exergonic. Exit energy is exergonic. Awesome. That's how you attack test questions, left, right, sideways. Perfect. And you notice, let me just talk about something. Notice the book never tells you that kind of stuff. It never puts stuff together like that, rarely. That's what sucks about books. Let's just go ahead and say it. Books spend so many pages, just plugging information in your brain. And sometimes, the pictures help, but yeah, they never really just put it all together. So that's why we have to have these discussions. And let me give you another key. One thing I skipped over my first year in college, I used to look at these diagrams and these illustrations and stuff, and I'm like, oh my God, that looks complicated. Let me just turn that page, right? Let me skip that. Well, let me tell you, a good figure, a good illustration, or a chart of some kind in a book, man, let me tell you, that's another secret to studying. Sometimes you can study a figure or illustration, and it could bring everything together. Pages and pages of data can come together in one picture if you know that picture well. So don't skip over some of those illustrations. They explain a lot. They really do, if you give them a chance. Okay, here's our monos: glucose, fructose, galactose. I normally don't ask you to memorize too many specific things. I do ask a lot of word association from you, but I'll be honest, I would memorize these if you can. Because a lot of times you're asked, these questions are cyclical, but a very popular question in A&P is which of the following are monosaccharides, and you're given like 5 choices. So I would know which 3 are monosaccharides here: glucose, fructose, galactose. And yes, they're known as a hexose because they have 6 carbons. So that's another key word. If you hear hexose, talking about a monosaccharide, just let me tell you. Or you could have a simple question like, is a monosaccharide a hexose 6-carbon sugar? And you're like, oh my goodness, I don't know. You never mentioned that. Well, I'm mentioning it now. Yes, monosaccharides have 6 carbons in their backbone. 5 in the backbone here. 1, 2, 3, 4, 5, and then one more right there. So all these angles represent a carbon. This is just the more simpler illustration. Here's the more complicated. So yeah, all carbs are going to have a mixture of carbon, hydrogen, and oxygen, all in different configurations, different, flip this and flip that. They all have the same thing though: carbon, hydrogen, oxygen. That's what a carbohydrate means. So those are the 3 monos, simple sugars. And we have a few 5-carbon sugars, these pentoses, like ribose and deoxyribose. We'll get to those later, but just to know those have 5 carbons. Here's our disaccharides, how we build them up. Notice all I've done is take the 3 monos, right? Here's our 3 monos again that we just covered. And if I marry them with another glucose molecule, we get all these special things. So fructose plus glucose gives us a sucrose, table sugar. Galactose gives us lactose. And then maltose comes from 2 glucose molecules put together. And notice if we're joining these 2 monomers, we're pinching off some water. So that is dehydration synthesis. There you go. And if we ran the reaction in the opposite direction, going from big, which is the disaccharide here, to small, that would be hydrolysis if we went right to left. And water would have to be put in, because we know that water breaks down sucrose, right? Water breaks down sugar, so we're putting it in. Awesome. And here's a little bit more of where that water comes from. If we take glucose again, marry it with fructose to make sucrose, which is a disaccharide, like we just saw in the previous slide. That's where that H2O comes from. Check it out. In order to make that bond, we have to lose water to make that bond. So losing water is not a bad thing. That water right here, metabolic water that's being lost, is just going to come in right here, and then you break something down again. So that water is not lost. It just, it's used in the cell somewhere else. Everything is recycled in the body, that's for sure. So again, if you see this picture on a test, will you know how to run that reaction both ways? Which one is synthesis, which one's hydrolysis? Which one's the disaccharide, which is 2 things joined, versus the monosaccharide, 2 independent monomers there? That's really all we ask of you of chemistry, just to recognize the basics that are going on. Here in this polysaccharide, this is a glycogen compound. Glycogen is a storage form of glucose. So when you eat that whole bag of Doritos, right? Or any of you guys been to Tasty Donuts, by the way? They got one over there in Ottawa and then one in down East Brainerd. If you've not been to a Tasty Donuts, you got to go like today. They have some incredible donuts. And yeah, they're full of sugar, of course, but it's glorious. So, after you eat a few donuts, are you really going to burn off all that sugar? Probably not. So where's that sugar going to go? It's going to zip itself up in a nice compact file, like a zip file in computer language, and make a glycogen molecule. And it's going to be stored in your liver and skeletal muscle for a rainy day. Not literally. You don't burn sugar on a rainy day. Anyway, I'm so full of stupid jokes today. Sorry. When I say a rainy day, I mean when you need sugar, the body's going to break it down again under this process of glycogenolysis to reverse it and give you back that sugar. So in short, this is a storage form of sugar in the muscle, the skeletal muscle. So when you work out, first 20 minutes of your cardio, what are you burning off?
Calories.
You're burning off all this stored sugar, this glycogen, right? And then after about 20 minutes, that's when you start burning fat. So give yourself at least 30 minutes of cardio so you can have good 10 minutes of fat burning. But that's usually the ratio there. Yeah, and so is it a good idea to leave the gym and drink a big Coke? You know, you don't want to be doing that. You just put all that sugar right back in you, all those calories. How about a bit nice Starbucks? Probably not. So enjoy, right? Enjoy that burning off that sugar. That's what's going to help your body get a little bit leaner if you want that. But anyway, glycogen represents a large polysaccharide storage form of glucose. We'll play with this one later. Getting into proteins, what's the keywords here? Oh my goodness, there they are staring you in the face. Protein, amino acid, peptide bond. Link those three words in your head. Anytime you see the word peptide bond, oh my goodness, he must be talking about a protein. What are proteins made of? Amino acids. How many amino acids? 20. How many proteins in the body? Holy cow, you can't even count them. There's so many variations of proteins. It's too many to count. Thousands of them. Proteins are all over the place. They act as carriers in the blood. They act as the structural tissue of almost everything. Proteins are everywhere. And what are they made of? Amino acids. Peptide bond represents how the amino acids join together. And here's another version of that dehydration synthesis and hydrolysis reaction, making a dipeptide. Okay, here's our organization of proteins we saw in lab. So the simpler proteins, primary, secondary, right there. Simpler structure there. So each one of these little beads you see is an amino acid, right? The little line you see in between the beads is a peptide bond. This is a polypeptide, right? But its structure itself is very simplistic, so it's known as primary. Where we get more confusing and more complicated, more advanced, is when parts of the protein are attracted to itself. So in lab, we do this fun little experiment. It's kind of silly, but it proves a big point. We take this bendable tube and we start taking, excuse me, a bunch of tacks, different multicolored tacks, thumbtacks, and we randomly just take a handful of colored tacks and start poking them in this tube, right? And the tacks represent each of these amino acids. Now, when one student does it standing next to another student, and then one table standing next to another table, you're never going to find someone that had the exact same arrangement of colors of tacks. It's all random. Well, think of that in the body. That's a question on that water worksheet. What ultimately determines the shape of a protein is the sequence of amino acids. The sequence, or in this case, in that example, the color of the tacks. Do we have a red tack next to a blue one, next to a white one, next to a clear one, next to a yellow one? It's all random. That just represents the different kind of amino acids placed next to each other or not. That's what I mean by the sequence. So all these amino acids, they could have 5 amino acids of the same kind together, and then one differently random here, another amino acid, and then 3 of another amino acid, 4 of another one, and then 3 independently of a different one. It's a whole different sequence. That's what determines whether you get this shape or a simplistic shape, because those amino acids are going to be attracted to each other, not just for the peptide bond. But think of this, if this were red right there and that were blue in our example, not that amino acids are colored, I'm just saying in our example, if the red and the blue were attracted to each other, what would happen to the shape of this simple primary? That red would go whoop, right over there and touch that blue and make another type of bond. And you would get a nice tight pinch or a tight coil like this, right? So that's how we get all this other kind of shaping. Parts of the protein are starting going to be attracted to itself, and they're going to twist and bend, giving you these shapes here, which are more of the tertiary quaternary. These end up being called globular proteins because they're very complicated, right? They're very advanced. Whereas these are called fibrous proteins. They're very simplistic in nature. So please know these examples in both lecture and lab. I promise you're going to get a question on those. The fibrous proteins are primary, secondary, giving us different fibers in the body and structural things like collagen, especially. That's what keeps our skin nice and good. And globular proteins are well advanced all over the body. This is, boy, there's some big players here. Some antibodies, hormones, enzymes. Big functions going on. And they're globular. They're more solid, whereas these are more like, up here, the fibers are more like strands. Okay, looking at enzymes oh my goodness, I can't even talk, specific globular protein. They're very specific. They have what's considered a lock and key mechanism of function. They're not used up in the reaction. What did I do here about bolding these words? These are hot topics, hot keywords, hot key phrases in all test questions. So when I build PowerPoint slides, I usually do things very specifically to clue you in. Hopefully you're seeing it when you study. Enzymes end in ACE. They speed up. They're not used up. They're specific, lock and key. All those word associations, right? Get to be really tight on word associations. It's a great idea. So for me, I mean, it's the same thing as highlighting stuff. But when you highlight stuff, that doesn't mean I want you to read the whole paragraph. I want you to link up just a small amount of words. There you go. So we're going to look at that lock and key. This is our enzyme. It's a protein, right? Not all proteins are enzymes, but all enzymes are proteins. Don't you hate those kind of statements? So this is a protein. What kind of protein? Is it a fibrous protein or a globular protein?
Globular.
Perfect, globular. Likely a tertiary. It could be quaternary, but just know that it has a 3D shape, okay? Quaternary just means that two 3Ds came together, by the way. Let me go back to that slide. That just means two of them came together. But mostly we'll be talking about tertiary when we talk globular. But anyway, it was a globular protein, just the same as some of these channels and carriers we're going to see in cell membrane, chapter 3. They're globular. Anyway, check it out. Look at the shape of what we call an active site right here. It's called an active site because it matches the shape to whatever we're trying to speed up. A substrate is a general chemical word for whatever we're trying to help. Whatever, it could be a polysaccharide, a disaccharide, doesn't matter. But it matches the shape right there. It hugs it real nice and tight. So that shape would match that shape. That's what an active site is. That's lock and key. And when it's locked up like that, that's called an enzyme substrate complex. Look at the nice little hug it's given. Isn't that sweet? That is our enzyme substrate complex when it's bound to the substrate. So if you get a test question, which of the following statements describes an enzyme substrate complex? That just means that the enzyme bound to the substrate, right? Using lock and key. So there's another example of a picture saying all the words you need. You just got to know how to describe it. Okay. And the enzyme, guess what? This enzyme will not be deactivated or used. It doesn't become part of the reaction. It's going to go on to help another, possibly it has to be the same lock and key, of course, but another reaction. It won't be used up. So that right there is not used up. Very important. I would definitely underline that right there. It is not used up. It goes on to do other work. Okay, and we know that proteins can become denatured if they're put in the incorrect environment, like high heat or acid. That just means all that beautiful bonding we exhibited between the protein itself is unraveled. So you change the structure, you automatically change the function. That's what we consider denaturing a protein. When we change its structure, we break those bonds. Not the peptide bonds. The peptide bonds are still holding it together. See? We broke these other bondings, these special bondings that are going on that gave it its shape. That's the denaturing. Okay, our last one here, nucleic acids will just take a second, but lipids are going to be our last big one here. Again, keywords. What do you see? Lipid, hydrophobic, mostly nonpolar. We say more or mostly nonpolar because some lipids, being so diverse, they might have an aspect of a polar end on it, right? Or a polar phosphate like we're going to see in the phospholipid, but mostly nonpolar. So if a molecule is 90% nonpolar, that's why we say it's mostly or more nonpolar, because it's going to behave in that way. Very diverse group, like we said. Here's all the things you need to know. Lipids represent triglycerides, phospholipids, steroids, and steroid hormones. Fat-soluble vitamins, again, like we said, and lipoproteins, high density and low density. So know that family of lipids. Now, this is not a lipid, but it's also nonpolar, which will come in handy in chapter 3. Gases are also considered nonpolar. They're not lipids, don't get me wrong, but they are nonpolar. So that's going to be in the same family of how they're brought across the cell membrane. That's what we're setting you guys up for by teaching you polar versus nonpolar. It's that alone, right? That factor that determines whether a certain molecule passes across the cell membrane in a certain way or not. So that we're going to see that coming up this week in lab, certainly, and then Thursday for lecture when we do chapter 3 in the cell. Whole bunch of energy in fats, twice more than carbs and proteins, lots of energy, lots of good insulation and padding, as you know. That's a good thing. Here's the monomers that we mentioned. There's the polymer as it builds up. I'm going a little faster because we need to get acid bases, like I said, in the last 2 minutes. Look at that. We got a carbon backbone. Excuse me. Look at all those hydrogens. Holy cow. Guess what all those hydrogens mean? That's a crap load of energy. You're eating like a hydrogen bomb, not literally, but you can consider it that. These solid saturated fats, they're like that. Yeah, they're going to have a lot of energy when you eat them, for sure. All that hydrogen. And then when you grab something packaged in the gas station, those beautiful cinnamon rolls or honey buns, and you look on that label and it says partially hydrogenated, what'd you just put in your body? You just put even more hydrogen in there, which means a crap load of energy that you may not be burning off. So yeah, it's gonna turn to fat again in the body. It's gonna be broken down, but also stored as fat. So yeah, there's some differences between saturated and unsaturated. Unsaturated or liquid at room temperature, like your oils and such, and saturated, will be solid at room temperature, like bacon grease, that kind of thing. Okay. Here's the one we like to play with, a phospholipid. We're going to spend a lot more time in chapter 3 on this, but I do want to at least introduce that. Look at that phospholipid right here. There is one phospholipid here, one head, two tails. Then you got several of them making one layer, and then another layer gives you a bilayer. This is your cell membrane right here. And if I told you the tails were nonpolar and the heads were polar, then simply put, would you agree that most of this membrane here is nonpolar? That's why we can say that the cell membrane behaves in a nonpolar way. It acts like a fence, a barrier. That's what it is. So we'll talk more about that in chapter 3, but recognize what makes a phospholipid: a polar phosphate head and two nonpolar fatty acid tails. And that's going to be our good intro into getting into chapter 3 for the cell membrane. All right, so there is one last one here, nucleic acids, made up of nucleotides. That's all we really need to say about that. Just know the examples here: RNA, DNA, ATP. And we'll come back to this in chapter 3 as well. Lastly, let me go ahead and do the, let me just skip through this. We've been through this. Let's talk acid and bases for just a minute. And I gave you that video link. It's going to actually probably explain it even a little further than what I'll do here. But real quickly, a pH is nothing more than a measurement of hydrogen ion concentration. So do know that definition. we're measuring hydrogen ion concentration. So anything under 7 is the neutral point, which is water. Anything under 7 is considered acidic. So the highest acidity, right? Which one would be the most acidic? Gastric acid or urine? The lower the number you go, the more acidity you get.
Gastric
Yeah,
acid.
gastric acid on this scale, at least in this example, is the most acidic. That means that gastric acid will give off the most hydrogen ions. So which will give off the least hydrogen ions here underneath water?
Urine.
Urine of these examples of acids. Yes, perfect. So that's the scale. 0 to 6.99 is considered acidic. Basic is 7 above 7, 1 to 14. So the most basic compound we get on this scale would be bleach. The least basic, if you want to be honest, would be the gastric acid, wouldn't it? But at least in these base examples, it would be seawater. So just know how to read the scale. The most hydrogen ions being given off here is with gastric acid. With bases, these give off hydroxide ions. So the higher number you get, the more hydroxide ions are given off. So in this case, it'd be bleach. All right, so here you go. This is the skinny on acids and bases. They're known as proton donors. They give off hydrogen ions, and they also release an anion. But that's the key. They give off hydrogen ions. That's what an acid does. And it's known as a proton donor. So let's go back to the scale real fast. Hydrogen ion concentration is the lowest you go. Here's the highest acidity, number 1. Or you could say 0.1 to be honest. The lowest acidity would be number 6 or 6.99. The highest base is 14. The lowest base is 7.01. So there's your ranges of alkalinity or basic. So bases, I know we're doing this fast. That's why I'm giving you that video. And a little time over here. Just give me 1 more minute. Bases are known as a proton acceptor, and they give off hydroxide ions. So you're going to need to review this. It's a lot to take in at the last minute here, but just a few keywords there: proton acceptor and hydroxide ions. Salts are neither acid or base. They have no hydrogen or hydroxide, do they? So salts are in their own little family. Last slide, guys. A buffer. A buffer is used in the body chemically to balance the scale, really. If you have a too acidic environment, a buffer is going to come in as a base and balance out that high acidity. So let's just take a brief example. If you take an antacid to get rid of extra acid in your stomach and such, what would that antacid be? Would it be basic or acidic?
A base.
Basic, right. If we're trying to get rid of acid, we want to put base on that to bring it more basic, right? To get it out of the acid range. So would an antacid increase pH or decrease pH? Again, where's the base on the scale? Is it higher or lower?
Higher.
As you go higher in the scale, higher number, you get more basic. As you go lower or decreasing, you get more acidic. So we're definitely be increasing the pH. So in a clinical scenario, if a patient took like 3 bottles of antacid, which you should never ever do, but if that happened, you would go way above the pH of your normal blood, and you'd be increasing the pH too much. You'd be above the 7.45 that your blood is actually should be going too basic. Yeah. So they'd have to pump your stomach to get all that crap out of there. So there you go. This same information will be presented in that video if you want to watch it later today. But that's all I had, guys. Thanks for staying a little late today. Sorry about sorry about keeping you. Really am. Any questions? I'll be here for a few minutes.
Thanks.
All right. Have a great day.
You too.
I have a question. This is Brenda.
Yeah.